Hello everyone. My name is Satyavikram Pratap Singh and I am NPTL TA, and for the course the Smart Grid is Basic to Advanced Technologies, and the whose instructors are Professor N.P. Pardisa and Professor Pranita Jena ma'am, and it's a 11 tutorial session, and the flow of this session will be such that we will go towards this some theoretical parts, and after that we will solve the some of the numerical in between also in the end also. So before moving to the lecture side, and this whole lectures means a whole session will be means important for solving your 11th assignment and also for your exam as well. So the main crux of today's session will be understanding of this energy management. Energy management in the all the senses. Okay, how we are going to do this energy management inside of this inverters and the DC and AC microgrid system. So the basics, coming to the basic system architecture, when you consider this AC and DC distribution systems, so mainly that is the grid interactive DC microgrid system, which is comprised of a PV connected, which is connected to the DC microgrid. If you see that this is a one bus bar is there, which is a DC bus bar, which is connected to PV panels, batteries, and a ultra capacitor, that is a DC generating sources. And in between, you can see that some of the converters are there, such as the boost converter, whose PWM is taken with respect to the MPPT. And second, if you see that the single H bridge bidirectional converter is there, and also in the ultra capacitor also, because you need the bidirectional power flow from the battery and the ultra capacitor, not in the case of the PV panels. So after that, you can see that this DC to AC converter is there, which is for connecting the utility grid for this AC generation, and in between you have a transformer based upon the AC what is being generated. If you see that there are two kinds of system are there, one is the grid side converter and second is that this is DC microgrid, which is connected to bidirectional converters, unidirectional or bidirectional. In the PV it is unidirectional, but in the battery and the ultra capacitor is bidirectional. And the grid side converter is basically the AC to DC converter, which is AC side is connected to utility grid and DC side is connected to DC bus bar for transmitting the power to the same level which is needed. In between, the transformer is also used. And this lead acid battery or lithium ion battery, these are considered as the storage system for in case of the DC or the AC microgrid system, which is utilized during this peak hours, and it is charged during the off peak hours. And the loads are also there. Loads, if you see that load 1, load 2, load 3, which is connected to relays, which can be means smartly operatable, so that the power consumption can be minimized during this during the peak hours. And so that you have two kinds of loads. One is essential loads, and second is the non-essential load. Essential load is such that which cannot be disconnected during the operation of the whole system, and the non-essential load, which is actually we also there are two categories: high power consuming loads and the low power consuming loads. In case of the essential loads also, essential loads are such as if you are operating the AC in the summer, it's a kind of essential during the summer, but is a high power consuming. So based upon the priority basis, you have to control the loads as well. Okay, so coming to the basic control system architecture, which is utilized for controlling this system architecture. So if you see that there are converter, which I have already told, that is the for connecting with this AC kind of system, you need a in between transformer will be there, and after that you need AC to a DC to AC converter. Okay, and which have a certain inner control loops. Okay, inner control loop in what sense? So you have a central power flow control strategy. Why? Because there are various generating sources, such as the PV is there, you have a battery is also there. Okay, you have a ultra capacitor is also there, and during the this battery is at a low condition or the ultra capacitor at a low condition. So in that situation, this extra power which is being needed, it can be come from this AC side as well, AC side as well, to meet the demand at a DC bus bar. So if you see that in the power control strategy, what is being monitored actually, if you see this PV and the IPV, which is going into the MPPT for generating the voltage at a maximum power point, so that the power is max. Okay, so this control goes into this power flow control strategy. Second is the SOC of the battery. And third is the VG, PLL. It is the theta value which is coming from the monitoring this VG. VG is the grid side voltage. Grid side voltage. This is important for generating the pulses for the inverters, that is the AC to DC converter. And also you have this V bus bar, V bus R reference, and the V bus. V bus is also being maintained, because if you are converting this DC to AC, suppose there is a bus bar voltage is there, bus bar is there for conversion, then you have a DC to AC converter. This bus bar voltage should be maintained. Suppose it is a three-phase system. So the voltage needed here is a 550 to 650, because the V that which is being generated, VDC is equal to VAC is equal to MVDC by 2 for this three-phase system. Okay, so 550 to 650 have to be maintained. How it can be maintained? It can be maintained by injecting the power from the battery and taking the power from this panel, solar PV generation, by operating at the VMPP. So all the system have to be monitored at a central point. So if you go into the deep of this internal control loops, you can see that this is a battery PWM generation, that is the battery monitoring system, and this is actually this ultra capacitor monitoring, ultra capacitor control, if you can say. And this is the grid side control. And last, if you see that this is actually the MPPT of the PV generation. Okay, so in the first, if you see that the IB is being monitored, IB with battery actually being monitored, and the IB reference is in your hand. In your hand means when to discharge and when to charge. Based upon the control strategy, that is the IB reference, it battery should be charged or discharged. Suppose this is a battery. Okay, so how you can control? You can control by, suppose this is giving power. It is giving power. It means that IB is in this sense, because the IB is greater than 0. If IB is less than 0, it means it is charging. So by changing the IB reference, that is the negative or positive, you can charge and discharge this battery. And in between you have a controller such as PI controller, and the rate limiter is also there, because you have to compare with the triangular signal. If your value is higher than this, so there is a no thing to means compare. So if they have to be in limit in between this triangular, suppose it is 0 to 1, then your limiter should be also in the saturation, that is 0 to 1. Based upon that, the switching pulse is being generated. Same is the case with the ultra capacitor as well. If you see that the reference is being observed with respect to the DC bus bar and the same controller, then the PWM generation can be there. And the third is, if you see this VG, that is the grid side control of the inverter, VG is being monitored. VG, where it is being monitored, suppose this is a DC bus bar, then you have DC to AC conversion, then you have LC filters. After that, it is being connected to the grid. So this VG after the LC filter, it is being monitored through the PLL for the synchronization of all the pulses. Okay, then it is compared with the IG reference, because the main thing is you have to generate current voltage should be monitored. If it is a grid connected system, the voltage reference will be same as the grid current, but the grid voltage, but the current you have to be changed based upon the how the generation in the PV is there, how the bus bar voltage is being maintained. Based upon that, this IG reference should be changed. Okay, then it is compared with the IG, then the PWM pulses will be generated for the in this inverter, this AC DC converter. And the last point, if you see this PV have a special character. It's a unidirectional converter is being utilized, and that converter PWM is being generated by comparing the reference of the IPV and the VPV. If you see this VMPP is generated, then it is compared with the V bus bar, and the VV and the V bus reference is generated. Then the controller is there. After that, the everything else will be same as compared to the other, that is the battery PV. So there are three types of controls. If you see, that is the battery and the ultra capacitor have one type of controller for the charging and discharging by changing the IB reference, IUC reference. And the second is the grid control loop. Grid control is being used for the synchronization of the current signal. Second thing, synchronization of the voltage signal, because the change in the voltage which is being generated from the inverter itself, it should be same as the grid for the synchronization. Okay, it is being tracked with respect to the IG. And the third is the PV inner control, which I have already told, that is the for the operation at the MPPT. Then this certain control algorithm should be there, such as a PNO method is there, and you can say INC method is there, incremental conductance and perturb and observation method. These are the for the MPPT control. Okay, so these are also important. And the most important thing is the power flow control strategy, because the all systems are there. So you have a PV also, you have a battery also, you have a grid connected system is also there, grid is also there, you have ultra capacitor is also there. So this all the system are generating sources, from the one side to the other side. It is all are the generating sources, and when to generate how much amount, it should be have a central control strategy. This central control strategy is must. Central control strategy is must by observing the all the references, such as the IPV reference or VP reference. First, second is the IB reference, battery, for the battery. Third is the IUC reference by checking this, and the fourth is the IG reference. So these all our references are being checked and the monitored, and it is in your hand what reference you should give at a particular situation. Okay, so main feature of this power flow control strategy, that the main crux is the peak demand reduction, that is the decrement in the main peak powers during the peak times, such as the morning peak or the evening peak, and the smooth transition between the different modes. Suppose that it is operating initially the PV is generating more, it should go to the grid. If it not generating and the battery is also at a lower SOC, suppose it at a SOC is equal to 5% in the lithium and battery case, so grid should give the power. So this kind of transition between the modes is also important for the smoothly transition phases. And the effective control and management, this also control, because you have to give the signals based upon the same operation at that particular time, because the time samples need to be considered. And the fourth is the reduces the stress on the battery, because it should not be overcharged or over discharged. That strategy is also being monitored with respect to the IB ref. Increasing the life of the storage system and the covering the grid connected system, this is also and the islanded mode. And the last is the unity power factor feeding to and drawing from the conventional grid. Okay, so main crux is the you have to maintain this Q is equal to 0, or you can say that IQ is equal to 0 if you are converting into ABC to DQ frame. So ID is same as the based upon this currents you have to compare, and the IQ should be 0. Okay, in the control system you have to feed like this. So I have one question related to this demand side management, that I have told you that the peak reduction and all. So there are six options are there, six options the right side, and the curves are there. You have to match with this correct terminology. Suppose the first is there, you have to match that what it is depicting. Okay, so this is a good exercise for you for the demand side management, for means comfortable with the terminology of the all the systems, such as the load growth, flexible load, conservation, load shifting, valley filling, and the peak clipping. Okay, so I'm giving you 5 to 10 minutes to solve this question. Just make sure that you should solve this question. This is very important for if you are considering this demand side management. Okay, in case of any doubt, just let me know, or you can write in the chat box as well. Anybody? Um, if you got any of the correct answer, just write in the chat box that A is the third is matching with the A. Like that, you can write in the chat box. If you got any of the correct answer, one, two, or three, any. Okay, I've got one answer. That first is F. First is F, second is E, okay, sixth as A, okay, fifth as B, okay, fourth is C, third is D. Okay, actually that's correct. If anybody else trying this question, anybody want to attempt? Okay, let me jump to the solution part. It's already 5 minutes. So that's correct answer. Uh, so the if you see that first option, that is a peak clipping. Peak clipping is such that if you have the peaks at the particular time frame, suppose you have a load curve. This is the power versus time curve, and in typical power load curve generally look like this. Suppose this is kind of thing, and this is like this. So this is the your morning peak. This point is actually morning peak, and if you see this point, this is the evening peak. And this morning peak actually occur in between 6 to 8:30 nearly, and this evening peak, nearly evening peak duration generally occur during this 6 to nearly 9. Okay, so these are two peaks which generally been observed in the load curve, that is the morning peak and the evening peak. Main crux here is the average loading. Suppose this is the average load you have, average load. So you have to develop, mainly research is such that ki how to remove this peak to level this up, coming to this average load level. So in the peak clipping, that is the same during the mechanism, which is such as you have a battery. So during the peak hour you can discharge your battery, okay, and you can charge during the off peak hours. Okay, this is the main crux of this peak clipping. So suppose this is the reference at which you want to reduce this P. So from the P max, so this is a kind of peak clipping. You are clipping the power this much power you are clipping. And the second is the valley filling. Valley filling is such that suppose this is the two durations are there. This is your peak duration. This is your peak duration, and this other is the off peak duration. Okay, off peak duration. So what is happening that you are unutilizing the extra power during this off peak hours, but you are utilizing extra during the peak hours. What is the main important? You should charge your means you should increase the load during the off peak hours. Okay, so to a certain extent, suppose you have a battery, you can charge during the battery so that the load in the off peak hours can increase, and in the peak hours you can discharge that battery. Okay, this is a valley filling. And second is the load shifting. Suppose this is a kind of peak is there, so you should shift this load. Suppose this is from 6 to 7 and 7 to 8, so you should shift from this 6 to 7 duration to 5 to 6, so that you can fill the gap also, and you can reduce the peak also. This is a kind of load shifting. And third is the conservation. Conservation says that you should reduce the all time frame power, whether it is in off peak hours, it is on peak hours, so that the you can generating capacity can be reduced. Suppose you have a two generating sources as a particular bus bar. Okay, what happened that the one generator got tripped, and then you have to supply the load. Okay, so load is designed, the congestion or the current which is flowing into the system is designed in such a way that both are operating, that is the IG1 plus IG2. What happens, this first one and two, IG1 got reduced to 0. So what will happen that IG2 have to supply the whole of the current of the load, but this causes stress on this generator too, so that you should conserve this power, and you should reduce the all the load during the all the system, all the time frame, so that they are reducing the stress on the particular generation system. And the other is the flexible load. If you see that this is a dotted, so all the loads which is in your home are controllable loads. Suppose you have oven, so oven you can operate in the off peak hours, no, because it is a consuming high amount of power when it is operating, so you can use in the off peak hours. So it is a flexible when to operate in the oven. Suppose you have a air conditioned system, So air conditioning system can be operated on the other time frame, but suppose first suppose you want to operate from 6 to 7 during the peak hours. So you should operate from 6 to 6:10 and switch it off for 6 to 6:15. Then after that 6 to 6:30 you can operate. So based upon the time slots, you have a flexibility that when to operate these loads. Okay, and the other is the load growth. Load growth is such that when the both generators are operating and the load is less, so the extra power is generator is a kind of means wasting the extra power. Where it is going, it is a form of the heat. So based upon that, you should increase the load at that particular time. Okay. So this is a being recommended in the evening hours. From that, the suppose the farmers are there, they actually do the irrigation in the evening peaks. Sorry, not evening peak, in the off peak hours in the night itself, and they are incentivized during the operation. So they have given the tariff also less tariff during that particular time frame, or zero tariff for the irrigation. So generally it is been recommended that they should do the irrigation kind of part in the night itself. Okay. So this is a flow chart of this proposed PFCS, which is being explained in the NPTEL lecture itself. Here only I wanted to explain that you have a multiple kinds of system. You have a generating sources, battery, ultra capacitors, and loads is also there. Essential loads, non-essential loads, and the no load or the ideal condition. And you are also absorbing the power at a particular duration, or you are supplying also. So if you see that there are multiple control strategy for comprising of the all the system into the action. Suppose the grid is there, whether it is available or not. By checking the power generation from the PV, whether it is supplying the extra power which is there or not. If it is not supplying the extra power, you have to borrow it from the grid itself, so that to compensate the extra load. So that is the all the considering the strategy. Also you have the peak hour strategy, that to you, if you have essential and non-essential, essential, non-essential, and also in that essential you have a high power consuming loads, low power consuming loads. In the non-essential also you have a high power consuming and the low power consuming. So you can shift this high power consuming loads in the off peak duration time. So this is a kind of flexibility. So here you have to operate this monitor the SOC of the battery also, SOC of the battery which is connected to the PV. Okay, so this is also should not be reduced. Suppose you have a lead acid battery, the minimum SOC you have to maintain in between this 55 to 50 to 55% minimum SOC. And in lithium ion you can go up to 10%, 10 to 20 or 30%. So that is a not issue with the lithium ion. But with the lead acid you have to maintain the SOC also at a 50 to 55%. In that situation you have to monitor the SOC of the battery as well. And the second thing is that when you are monitoring the SOC of the battery, you have to check the PV and the load as well. And the second is the MPPT operation as well. Suppose your grid connected system is there. So extra power which is generated, suppose the PV is there, battery is there, you have a ultra capacitor is also there. So extra power which is being if it is generating, then the load. So this extra power can go to the grid. Okay, if it is a grid connected system. So if it is a islanded situation, what is where it this extra power will go? In that situation where P battery, P ultra capacitor is less than this P load. Suppose this extra is being generated is greater than this, and the islanded situation is there. So what happened that your PPV will not operate in the MPPT operation, it will be lower than that, so that it can balance this extra generating source, so that it should not generate the extra which go into heating, or it is also as a isolated system, so it should not operate in the MPPT. So this is situation with the multiple types of controller into the system. This is also kind of research area, that how you should design the this AC to DC conversion or the DC to AC conversion by comprising of the all the AC microgrid system and the DC microgrid system into one system by implementing the this novel control strategy of the system into the system. So there are two operations which I have already told, that is the peak hour mode. Peak hour mode is that the priority is either to supply or the draw the minimum power required for the essential loads in the grid interactive DC microgrid by the ensuring the DC voltage within the in these limits. And the off peak hours, if you see this conventional grid is there, it can deliver the enough power at a low cost, okay, in the off peak hour. So if the generation is low, generation is less than the demand, in that situation, the grid should supply the extra power, that is the demand minus generation. And if it is operating in the off-peak hours, the tariff should be low. Tariff will be low. So in this situation, the cost which is of electricity should be it should be lower. So that is feasible solution, that you should take the extra power during the off-peak hours. And the second is the charging of battery. Actually, it is preferred during with the full load supply from the grid, so that the stored power can be utilized locally when the peak demand of occurs on the central system, that is CGs, conventional grid. Okay, that is the however these CGs have been driven into the peak demand, which increases stress on the and the discharging of the full SOC of the battery. So basically, the off peak hours you can discharge charge this uh, battery itself, so by by utilizing the low tariff during of electricity during at that particular time. Suppose there are isolated mode, what I have told you that it should not operate in the MPPT, so it's operating at a off MPP situation. And the second thing is that this DC microgrid operating under the all worst situation, like the generation become lesser than the load or SOC of the battery is very critical. So in that situation, it should be in the ideal situation. Neither it's a delivering, neither it's absorbing, because it's a no grid is available and the SOC is also at a lower value. So you should not have available availability of the power is not there. So you should be stand still. The battery should be at a stand still situation. It should be not be absorbing any power, or it should not be any delivering extra power. Okay. So coming to this next problem, this is the small problem related to the peak saving, peak saving, and you have to tell me that what additional capacity being required from the battery to achieve this peak saving of the. You have few minutes to solve this question. Okay. If you get the answer, then just write in the chat box. And if you are facing any problem while solving, just let me know. Okay, I got one answer as a 120 kilowatt. Anybody else who wanted to give the answer? Um, Yadima and Devendra, Umar, any answer from you guys? If you're trying also, just write in the chat box that yes, I will give you some few minutes also to come to the solution part. Okay, let me come to the solution. Okay, what it is saying, let's read the question first. What is saying that a commercial building is there which has a peak electricity demand of 600 kilowatt. It means that the peak is 600 kilowatt. Okay, and for the certain duration operation, what I've told into the load curve also, suppose this is the actual load curve, this is the peak time. So for the duration, this peak is actually 600 kilowatt. And to implement a peak saving, the building install a battery storage system, okay, which is capable of supplying 150 kilowatt of power. So maximum battery power which can be supplied is equal to 150 kilowatt. Okay, so if the building aims to reduce its peak by 30%, suppose this is the peak and it is 600 kilowatt, and they wanted to reduce by 30%, it means the new peak will be 70%, that point 0.7 of the 600, that is the 42, that 420 kilowatt new peak. So how much reduction is being there? That is the initially it was 600 and it got reduced to 420. How much change has been happened? That is the 0 and 8 1 180 kilowatt change has been there, and this 180 have to be supplied from the 150 kilowatt. But if you see that its a maximum capacity is 150 kilowatt. So what is trying to say that if the building aims to reduce its peak, how much additional capacity does the battery storage system need to provide? So 150 was there initially, but 180 it is demanded. Okay, so the extra which have to be there is a 180. Okay, so extra supplies one is which is being installed, that is the 150, but the much additional capacity that is needed, does the capacity storage need to provide, that is the 30. That is the 150 is already there, 180 need to be there, but the 30 kilowatt is actually needed. So here the options are not correct. The 30 kilowatt is the answer, because the additional, it is asking the how much additional capacity does the battery storage system need to provide. It is a already you need the 180, but the 150 kilowatt actually it can supply at a one stand. Okay, so the 30 kilowatt is extra to be generated. Okay, so coming to this next one, if you have any doubt in this question, just let me know if you have any doubt. Actually, what is saying that in the power terms, not in the energy terms. So energy, suppose the battery it can deliver a 120 kilowatt of power at a one instant. But if battery capacity may be higher, suppose it have a 300 kilowatt hour. So 120 it can deliver at a one instant of time, but it is needed to deliver 180. It can do in the few hours itself, or you can in the this few minutes as well, depend upon the rating or the C rates, how much amount it takes to give the power. Okay, so coming to this one most important topic, that is the types of HIL experiment, that I wanted to tell you that because there are multiple case studies which is being means depicted in the slides and the lectures itself, but you have to understand that what is actually the HIL and the this CHIL or the PHIL. So actually hardware, so what initially what I have told, that you have a grid and you have multiple interconnected systems in between of that. Suppose there are one microgrid is there and other grid is there, and you have a generating plant. Suppose this is other plants, suppose other microgrids are there, so each systems are actually being connected. Okay, so this is a high power level devices, means generating sources, that is 50 megawatt, 50 kilowatt, and this 10 megawatt. This kind of generating systems are there in the actual grid scenario. So you cannot test these systems in the real time environment. So what generally researchers do, that they do test in the real time using RTDS systems, real time digital simulations. So if you use the MATLAB and if you run your script file, you can observe that it is taking actually showing 2 seconds, but it is taking 1 hour to means solve that simulation, or 10 minutes to solve the situation. So this is not a real time. This is not a real time. If it is a 2 second in the real time, it's also should be 2 second in the real scenario also. This is done through RTDS system using FPGA boards which are there inside of this RTDS systems. So what is HIL? Actually in HIL simulation, the hardware devices are interfaced as to a real-time simulator, which is actually shows the clock which is in there in the MATLAB environment, and which is actually that time which is in the real environment, which contains the rest of the modern necessary to test the device operation. And the first one is the HIL. This HIL simulates the offer a cost-effective and the safe method to test the physical system. Why? Because you cannot test this fault at a bus in a real scenario. You cannot create a fault, but you can test in the HIL system. And the second point is that HIL simulation can be open loop, where the signals are sent to the RTDS. What it means, that if it is a RTDS system is there and you have a controller is there, you can send the directly signal to RTDS. This is the open loop, but you are not receiving from the RTDS system. But the closed loop is also there when where the response of the device is fed back to the RTDS. Okay, so controller is giving the power this signal to RTDS system, and also RTDS system giving the this signals to the controller. Okay, so suppose grid connected system is there. You have two quantities. One is the IG, one is the IG star. IG star is the reference how much power is to be delivered at a what particular time. So this IG star is being suppose it is being calculated using certain algorithm. Then it have to be transferred to the controller so that it can modify. Okay. And this HIL simulation are the two types. One is the control HIL, second is the power HIL. The control HIL, if you see this control HIL, this simulation diagram, there is a no power conversion or there power devices are there in between. If you see there, you have a real-time simulation. Only device under test is there. Only you are transferring the digital to analog signals, digital signal or analog signal. Okay. So in the real-time simulation which is happening in the RTDS system, you are transferring the signal. Suppose you are transferring the digital signal by using the DAC converter. Then you can amplify that signal because it's an analog, low analog with the noisy signal. So you can amplify that, and it can be sent to the device which is being under test, and it can receive from the this device under test using ADC converter. Okay, to and it is already being fed to the RTDS system. So here no power stage is there in between this HIL. Power stage is not there. So this is a purely control HIL, which is controlling the by giving the signal digital or analog. Okay, and here the exchange of the power voltages are only up to the plus minus 10 volt. Okay, this is a low power. Okay, but coming to the power HIL, you have a power conversion stage is also there in between. How? And you can say that suppose this is an amplifier is there in between, that is a scaling factor is there, and you can send this power to D to A converter. Suppose in the real time simulation what you are observing that it's actually 2 volt signal, but in the real environment it is a 230 volt. Okay, but it is transferring it's a mainly it is a 5 volt operation is there into the this electronic circuits. So you have to change this 2 volt to 230 volt for the power which is for sending the power to the device which is under test. So in between you need a scaling factor. Scaling means you should have an amplifier where the this voltage can be increased, okay, from the 2 volt level or 5 volt level to 230 volt. So this conversion you need a power conversion device, power amplifier in between. After that you can send the digital to analog conversion amplifier and all. And also you need the voltage and current sensor which is also being transferred and then filtered. Okay, so basically this amplifier is a which is being used is of Synergia. Synergia is being used for as a power amplifier in for the scaling of this voltage and the power level. Okay. So coming to the one question related to this PHIL and CHIL, there are multiple options are there, statements are there. Just you have to tell me that which statements are correct related to CHIL and the PHIL. Okay. If you are got this point which I have already told. You have a couple minutes to solve this question. If you have any doubt in between, just let me know. Okay, I got one answer at C. C means 2 and 5. Correct statements are the 2 and 5. Okay, anybody else want to give the answer? We have 1 minute to solve this question. Okay, let me give the solution first. Actually, the 2 and 5 are correct. Uh, Let's read the statement first. That is the what is saying that. First statement is telling that the PHIL, CHIL strategies, they are aimed to reducing the electricity consumption during the peak hours to elevate strain on the grid and the prevent power outages. Actually, that is false. Why? It's just a RTDS system, real-time digital simulator. It is not connected with the grid, or it is providing any control strategies to the directly to the grid. But it is just for testing purpose. And the second point is that is a PHIL involves simulating real world grid condition by integrating physical power equipment with digital simulation tools, while CHIL focuses on testing control algorithm and strategies using physical hardware component. That is true. Because I have told you that it is integrate that physical power equipment, which is Synergia. Synergia is a power amplifier. And in CHIL, if you see, you have a control strategy outside the system. No power stage is there. That is true. And the coming to third part, that the both PHIL and CHIL rely solely on the energy storage solutions such as batteries, pump storage, and to manage peak demand effectively. That is false, because it involves all the grid condition. That is a grid from the thermal also, hydro also. You can simulate. You cannot directly use. PHIL, CHIL are primarily implemented by residential consumers and have minimal relevance in the industry commercial sector where demand fluctuations are less significant. That is false, because they use this for the testing, this industry. But they are not installed in the residential consumers, because they are just a testing test bed system. Fifth is the success of the PHIL CHIL initiative depend upon the effective communication, the cooperating among energy consumer, utility, grid operator to incentivize and coordinate load reduction effort during the critical period. That is true. Why? Because if you are using PHIL or CHIL system, you have this control strategy, or you have a actual power consuming consumers, power consumption or generation, which is actually at a that particular voltage level. So from that you can actually coordinate or incentivize by controlling this strategy. Okay, so this 2 and 5 are correct. Let's come to the other part. This is, other topic is the system analysis of the AC DC smart grid, that is structure of the AC DC microgrid system. Because I have told you that you have a AC generating system, DC generating sources also there, so you need a, and a hybrid microgrid is also there. So there are multiple components are involved into the system, because it's a kind of new system. Initially what was happening, that when the war of current was there, so Nikola Tesla was mostly favored because of the advantage. Most of the advantages were in the favor of the AC transmission lines. Okay, in the AC transmission system. So the at that particular time the AC was more favorable, because there are no this means conventional, if you see that this generating sources related to from the PV, wind and all. So this kind of problem that they do not face. So currently the grid situation are such that the more PV penetration will generate DC, and then we have a more battery storage system for reducing the peak, that is also DC. Ultra capacitor also DC. So these kind of systems are there. So and you have a wind also. Okay. So you have to convert from AC to DC in the wind, which is AC system. But you can see that this is a multiple devices which are operating on the DC level as well. So you are now having the combination of the AC DC, and DC is also in a huge amount, not in a less amount. So this is a, you have to multiple structures are there in the AC DC distribution system. So major component in that, that is the actually including loads, just generating lines, and the buses are there. And the second, if you see that the generating sources such as EVs are there, electric vehicles also connected, PV panels are also connected. And the third part is that is the renewable technologies, that is the various types of, suppose you have a wind, it can be of type 1, type 2, type 3 or type 4. So in between that systems also you have a multiple in subsystem. which is being utilized. So each converter, suppose the converter is there, there are different converters for the different applications. So this is a kind of key major components are being there, which is a variability is there, very much variability is there. So coming to this classification, there because we will go through the multiple means components of this AC/DC distribution system. So one is the buses, classification of the buses, that is AC buses and the DC buses. If you see that initial what you have studied in the power system itself, that there are three types of buses. One is the load bus, second is the generator bus, third is the this slack bus. And the slack bus is a not a means real concept. It's a just ki one generator is there which is supplying the transmission losses, okay, plus the difference which happens in the power demand and the power generation. So that generating source, this slack bus will compensate that. In the slack bus, if you see that the reference is also, how you know the reference, how much this voltage magnitude and voltage angle you should generate at that particular reference, what amount of it is needed. And in the load bus, this P and Q consumption into the system. And in the AC voltage control, that is the PV buses, the power and the voltage, but you have to know the Q and delta. Okay, so two parameters will be known and the two parameters generally unknown. You can find out from the known quantities. And in the DC buses, you have two types of system, that is the P bus and the VDC. And in the, if you see this P bus, the net DC power which is being generated from the loads or the DGs, it injected into the bus, which is known as the DC bus voltage, which is DC voltage which is unknown. Because if you are converting from DC to AC, you need a DC bus bar whose voltage is being constant, okay, which can be done through using a multiple component, that is battery or ultra capacitor or the PV. And in the second, that is the DC voltage control bus, that is VDC bus. This bus voltage is known, but the power generated at the bus is unknown, okay. So there are two concepts, that in the DC load bus, that is the P bus, your DC voltage is unknown, but the P is known, how much power is to be generated. And second is the DC voltage control bus, at which this P is actually unknown and the V is known, okay. So if you see in the right side image also, you have a AC load, DC distributed generator system such as PV, and the DC generators are in the DC bus bar, DC load, AC DC and the AC loads. So you have a multiple types of buses. Initially it was we are studying that AC buses are there, that is a PV bus, PQ bus or the slack bus. Now you are considering this DC bus bar also, that is the DC load bus, P bus or the VDC bus, okay. And the most important is the load flow between, suppose you have a AC system is there, we have studied already that the Newton Raphson multiple iterative solution method, that is a Runge-Kutta method, and others non-linear means approximate systems which is being iterative systems which is being calculated by, used for the calculation of the power and the Q or the V or delta. So these kind of parameters we already know. Now what happened, that you integrated DC into the system. Now this iterative system, that it iterative, this become more complex, okay. So load flow, if you see that for the proper planning, you need this load flow analysis by comprising of the both the system, that is AC system also and the DC system also. So it is a steady state analysis, you already know, that is determine voltage, current, real power and the reactive power which flow under given loading condition. And it should be done in the time ahead system, that is the, you have to check whether the power flow is there initially, okay. So what kind of power flow you have to dispatch, okay. And the third point is that there are multiple algorithms for this AC DC distribution system also. That is Gauss Seidel, which was initially also there, which we use for the AC iterative system, NR method is there, fast decoupled method, the FDLF method, and the Broyden method is also there. And the by Rx ratio, mostly radial or the weakly missed. So this kind of system, AC system, which cannot be applied to AC DC system, by using this Rx ratio, you can determine which to connect and which to not connect. Okay. And in the fifth point, if you see that this is a more complex system and the most non-linear system are existing into the system. Okay. In the if you see this power constant in the P bus, VDC, IDC is there. So if the power is constant and the VDC is unknown, your IDC is a one of the parameter which is to be determined. You can determine by IDC is equal to P by VDC, or VDC is equal to P by IDC. So this is a one kind of inverse proportional system. And if you see in the AC generating system, you have a power is equal to suppose I square R, resistive load is there. It's a one kind of system. So one kind of system I square R loss and plus this VDC IDC term, at which this VDC is inversely proportional to current if the power is constant. So this kind of system are generally exist, means normally it is initially it was one kind of approximate, you can do that by one time of differentiation, but now the case is different. You cannot just utilize the AC load flow analysis directly. You have to make more iterative solutions, or you have to come to the conclusion and you have to check that it is violating the limits or not. Okay. So coming to this load flow challenges, that is the various load flow challenges, that is modeling and the this various types of sources, types of power converters, and the prerequisite, that is the constants is also there. So load flow equation, that is the need to be determined. So in the first model, if you see this power converter model, that is the AC to DC voltage source converter model. If you see, this is the point of common coupling, and in between you have a ZC, that is the this converter impedance, because it is converting from DC to AC. That is the inverter side, that is the I, that is QC, and PC is being generated, that is the AC. And in the right side, if you see that DC system is there, this is Jth bus and the Kth bus, and the voltage at both terminals are the VKDC and the VJDC. In between RDC term is there. So I in between the DC system will be VJDC minus VKDC divided by RDC. This kind of system will be there, and this you have to model. You have to use directly this kind of system when you are analyzing the system. So what will be value of this VIAC, which I have already told you that it is a M by 2 VDC. Okay, and here they have taken in the terms of this RMS, and also in terms of this maximum value. Okay, so it's a root 3 by 2 root 2 M VDC. M should be less than 1. Less than 1 means it can be up to 0.9 M modulation index actually. And same with this VIPU and the MVDA how much you have to generate from the AC to DC, that factor you have to consider, and you have to consider the efficiency as well. So I is equal to Vy. So here Y is actually GDC. GDC means which is inverse of this RDC. 1 upon RDC, that is the difference. That is same what I have told here as well, where the GDC is 1 upon RDC. When you are combine all the equations, you will get this PC. By iterating this solution on the QC, that is PC tan phi, you will get at a particular all the instant that PC and the QC. This is also done by using the iterative method. You have a square terms also there, inverse square terms. You can have directly proportional terms are also there. So you can use this iterative method for solution of this. Second is the DC-DC converter model. You have a multiple types of DC-DC converter, that is the isolated is one of them. Non-isolated is one of them. Non-isolated you have already stated, that is the buck converter, boost converter, or buck boost converter. Multiple types of converters are there. In the isolated system, this is a in the isolated system you have a multiple type of system when you have a multiple this. This is kind of various converters are involved in this DC converter as well. And the equations nearly same. That is a forward converter is one of them. The forward converter is there. So in the DC, suppose you have a buck converter. By designing, you will use this output power is equal to D times of Vs, and in the boost converter you will use this same output is equal to Vs divided by 1 minus D. And you have to consider the efficiency term as well, because during modeling what we do, this PS IS is equal to P out I output, and I output, suppose you are determining I output, that is a PS IS divided by P output, this P output. Based upon that you can calculate this I output. And for considering the efficiency also, you have to multiply the neta factor for the conversion, because P output by P input is not actually the one, it's actually a factor. So you have to consider that factor as well. And coming to this LCC model, that is a line commutated converter model, because suppose you don't have the zero crossing in between, or you are not commutating at that is line commutated, this self commutation is not there, so you use this line commutated system while crossing the zero. So at that particular time you need this LCC distribution system between the bus interface. So in this scenario, the major control objective are actually not highly recommended or needed, but just you have to use certain equations for coming to some conclusions. Okay. Coming to this distributed generator modeling, there are multiple types of modeling systems are there. There's a type 1, type 2, type 3 and type 4. In the type 1, this is the DGs, the distributed generator are capable of delivering only active power. The only P is being actually being delivered from this photovoltaic fuel cells which are integrated to the main grid with the help of converters. And in the type 2, this capable of delivering this P and the Q as well. And these are the types of synchronous machines, congestion, that is gas turbine, and comes into this picture. And in the type 3, this capable of delivering only Q, because you use these synchronous condensers such as gas turbine for operating at a unity power factor. Okay, operating at a zero power factor, sorry, because the power here Q you are delivering but the P is not there. In that situation your synchronous compensator you can use, because it's a zero power consuming device, zero power only, it is like that, and it supplies only Q, so power factor of this device is zero. In the type 4, if you see, it is capable of delivering active power P but consuming reactive power, means Q, negative Q. Mainly the induction generators which consume negative this reactive power, which is used in the wind farms, wind technology, that is type 1, type 2. And there's all these types of the DGs which are modeled, it having this PV DCs or PDC DCs or PQ DCs or P-type DCs, if you following this types as well. So these are the types of this DC, this distributed generator models. How much power is being generated, how only it is generating this Q. Okay, one question is there, that is can you explain why R by X ratio is not valid in the AC/DC? Okay, what happens that this R by X ratio having certain limits. Suppose it have a certain factor which is comprises that this is a strong grid. Okay, and one factor is Y which is considering as a weak grid. Okay, what happens that you have a two buses, you have a AC bus, you have a DC bus. Okay, and at DC bus you are connecting this battery, you are connecting PV by using some internal converters, and in between you have a DC to AC conversion device. Okay, so strong grid, what is mean by strong grid? Strong grid means how much generation, how much demand is there, it should all be generated and supplied from the grid. Okay, but what happens that here the demand is also a one kind of generating system which is being generating and giving the power to the grid as well. So the net current which is being needed, it got reduced. And this is the one scenario. And the second scenario that If the generating source is not generating that much, but it is modeled in such way that by comprising this generating source at that particular time. So in this situation, what happened that this take the power from the grid as well. Suppose you are considering the battery and it is in discharge state. So for charging this battery, you need the much more extra power from the grid as well. So this kind of system, this R by X ratio, which already you are defining for this AC distribution, that what is being generated, it will be directly given to the demand. But in this situation, you have a multiple sources at the DC terminal, which is generating also generating AC and also considering AC. So in this situation, you have to this reconsider this factor that what to use in the R by X ratio. So in AC DC distribution system, so you have to modify. You have to modify based upon the what is being generated at that particular situation, considering that it is a strong grid or the weak grid. Okay. So the basic step for the load flow formulation, that it have a mathematical model which I have told you for the VSC, you have for the DC DC conversion, for the P and this compensator as well, that is a LCC, line communicated converter. And the second is the mathematical modeling of these various types of loads. Loads means you have a multiple loads. Suppose you have a trim lights are there, and it's a kind of P kind of system, PQ kinds of system. It also consume P and consume Q as well, because the power electronic converter is there. So this kind of load will be defined in the P type load, P and this PQ type of load, P minus Q type of load. That kind of system you have to categorize. And this modeling of the renewable generator, that PV type, VDC, PQ or the P type. Okay. And the last is the suitable for this sequential approach to determine simulate, because you can use the NR method or you can use the FDLF method. So based upon that, you have to iterate and come to one of the solution. From here onward, I have some basic question related to some small topics. So there are only two statements are there, and you have to tell me that which statements are actually correct in both, that is the 1 and 2. And like that, I have nearly 10 to 15 questions are there, which I wanted to means, reconsider before going to final exams as well. So there are two statements are there, and you have to tell me that which statements are true and why. White component, you can open your mic and tell me that, or you can write in the chat box as well. Yadamma, I think I have answered your question related to that R by X ratio, and if you are comfortable or you are having doubt now as well. Okay. Okay. Okay then. Okay, these are the statements based question. Just you have to solve and to check that which statements are actually correct and which statements are false. I will explain the reason. These are the basic question, but you have to check before going to the exam. So first question, don't take lot lot of time for solving these questions. I got one answer that A is correct. Anybody else want to give the answer? Okay, I got one answer that B is false and A is correct. Anybody else want to try? I will give only 1 minute for these questions. If you can try, just tell me that A statement is true or A is false, or B is true or B is false. Devend, Shibna, anybody want to try this question? Okay, let me give the solution. Actually, A is correct and the B is false. Just read the statement that what is saying that load shedding strategies are implemented to reduce the non-critical energy uses. There, I have told you that there are two types of energy uses are there. One is the critical and second is the non-critical. Critical is these are the high consuming loads means, and non-critical energy uses actually they are not high power consuming. So load setting strategies which are being implemented it to reduce the non-critical energy uses. Okay, so non-critical in the sense ki these are the critical loads which have a high power consuming loads, and the non-critical loads are energy uses that you have to reduce that. Because if you are operating, if you are having the refrigerator at that particular time, these are the high power consuming and the critical loads. So what you do, you reduce the power in the non-critical stages. Suppose you have a multiple fans are there, suppose two fans are there, you can switch off one fan, you can save that energy, but you cannot switch off the refrigerator because it is must at that particular time. So what do? You should reduce this load setting done in the this non-critical energy system. And if you read the second statement, what is saying that large scale battery storage system are directly connected to the main grid. Actually, that is false, because if you see this main grid is there, you in between what you have a LC filter, then you have this DC to AC conversion system, and in between also you have a DC to DC boost converter is there in one form of system, and after that before that you have a PV. So you have MPPT control as well. So this is a not directly connected. In between you have a multiple stages. Okay. So coming to this next type, what if you see study the this reason as well, this load setting strategy, it involves deliberately reducing the consumption of the non-critical energy loads during the peak time or emergency to maintain grid stability. This strategy helps to prevent the widespread blackouts by prioritizing the essential services and reducing the strain on the power grid. Okay. So this is second question on your screen. Uh, just try this. Any guesses or any answers? Okay, Sibna given one answer that both are true, and this Dharni is giving A as a correct answer. Okay, let's come to the solution part. First statement is that microgrid with distributed generation sources can operate independently during the grid outage. That is actually true. True why? I have told you one situation that when the systems are again grid connected. In the grid connected system, you have a suppose this is a DC bus bar, and this voltage you have to maintain by suppose this is actually DC bus bar is there, which voltage you have to maintain, and PV is connected, and after that you have this DC to AC converter, and then it is connected to with some mechanism with the grid. So you in the grid operator system, it's fine. It's a PV is operating in MPPT and battery is there. It is supplying the power or absorbing or discharging. It is fine. If the extra generation is there, then it is sent it to the grid. What happened when the isolated system is there, oil ended system is there? In this situation, this PV need to be need not to be operated at MPPT. So by controlling this mechanism, this non-operation at the MPPT points, then you have to convert in the this VMPP not operating at the VMP or IMP. In this situation, you can do this load balancing. Okay. So microgrid with the distributed generation can operate independently during the grid housing. First statement true. Second statement is saying that traditional centralized power plants are exclusively relied upon the backup power supply. That is false. Why? Because this traditional, if you see that centralized power plant, suppose you have a hydro power plant and you have a coal-based power plant, they actually don't need any battery backup. That battery backup is for the different use. Here they use the coal, they generate this thermal energy, then move this turbine and then utilize and send the power. That is, the coal is such that one of the unit that they can generate this power by injecting high amount of steam. You can generate high amount of power. Less steam, you can generate less amount of power. So this backup supply is not there, because if the less generation there, you cannot switch on the battery at that particular power plant. So in that centralized power plants, they are not relied on the backup power supply. They are dependent upon the some external sources such as thermal energy from this coal. Okay. So coming to this third question, just read the statement and let me know. Okay, got one answer that maybe A is correct. Very important safety. Anybody else want to try? Okay, Shivna is saying A is true. Okay. Oh, let's go to the solution part. That what is saying that first statement, that predictive maintenance algorithm, okay, PMA methods are employed to monitor HVAC systems and prevent equipment failures. Actually, that is true. Why? Because the predictive maintenance algorithm says that they actually take the condition into the system. That is, suppose the HVAC systems are there and other systems are there, they actually monitor that at what particular situation they can fail. Okay. So predictive maintenance algorithm, that suppose it's a wear and tear can happen after 20 years. So they know through the algorithm that suppose first year it got wear tear to certain percentage, then second year it got certain percentage. So based upon that data and the initial data of the 20 years, that you can predict that up to what time duration it can means sustain or can operate in the proper situation. Coming to this B part, B statement, that static energy uses reports are generally periodically without utilizing the real-time data. Actually, that is false. False in what sense? Because the energy uses reports which is being generated, they actually utilize this real-time data as well. Okay, so this is the actually real-time data. Suppose today is the 7th April. So for this means a whole March month data they have analyzed and tell that the what amount of static energy has been consumed and what was the peak is there and what time it got occurred. So that was actually this real-time data at that particular time. And based upon that, the predictive that prediction has been done to how to counter that situations as well. So coming to this next question. Next question is related to home energy management system, which is explained in the third or fourth tutorial session. Try this question. Okay, is true. I got one answer. Two answers have that is true. Okay, let's come to solution part. That home energy management system actually integrate IoT device and smart meter to coordinate appliances operation. That is true. Second is that appliances operate independently without any communication or coordination. That is false, because if you have a multiple devices connected system, then they should communicate with the central controller. Suppose this is actually oven is there. Suppose you have a refrigerator is there, and you have ACs are there, you have trim lights are there, you have a fan is there. So it data is already given to this central controller. It will check whether it is a peak hour or not by observing the load curve, previous load curves. So based upon that, they will communicate and coordinate that which appliances should be off that particular time frame. So coming to the next part, this question is related to advanced metering infrastructure, and you have to tell me which statements are true or false. Okay, A is true. Okay, I got the answer. So let's come to a solution part. That first statement saying that advanced metering infrastructure enable remote meter reading, facilitate accurate billing and the timely outage detection. That is true, because if you see the advanced metering infrastructure, you have central controller is also there inside of that that features as well, and you have a multiple homes are there which data has been transferred to the central management system, which observes the data and determine which is the high power consuming homes are there. So at what rate they can send the power, how can manage their congestion as well. And the second is saying that the additional analog meters provide the same functionality as AMI but at a higher cost. That is false, because they don't have this advanced metering infrastructure as well. They call central controllers as well. So coming to this next question, please solve this. This is related to load forecasting. Okay, I got one answer that is true. They win if you want to try. Okay, I got one more answer that both are false. Uh, okay, let's come to the solution part. That first statement, what is saying that the load forecasting uses historical data and predictive modeling to anticipate future electricity demand. Because suppose today is 7th of April is there, what will be the energy consumption at 8th of the April. Okay, so 7th April have a certain load curve data. Okay, suppose this is P versus T curve, and before that, suppose on 6th, on 5th, on 4th, on 3rd, they also have certain data of this P and Q, P and T, P versus T. So what they do, they actually read these data and they predict one load curve based upon the previous load curve or for the 8th April. And actually that is important for managing the how much power need to be transferred from the generator as well, because how much demand is there at what time. So based upon that, which generator scheduled to supply at that particular time, that need to be determined in the pre-advance. Okay, so this first statement is true that this is forecasting done using the historical data and predictive modeling to anticipate the future electricity demand. Second is that utilities rely solely on the current demand data without forecasting future trend. That is false. Because if you don't know that what you going to do on the next day, so you can do the scheduling from the any of the generator which are already being operating at a maximum limit. So to avoid that, the pre-scheduling is always done. Okay, so this is the next question. This is related to some lighting fixtures which is being installed in the houses as well. Anticipate means oppose. No, no, no. Not anticipate means predict. Predict means yeah. Predict means कि what electricity need to be consumed on the next day. Based upon that, the scheduling of the generator being done on the previous day itself. That which generator should operate at what particular time to avoid any congestion or any related issue, any other issues. Try this question. Okay, I got one answer that A is true, one more answer that B with no idea. So let me explain you. What the first statement is saying that the LED lightning fixtures are installed to replace traditional incandescent bulb, resulting in significant energy saving. So what happened that you have a multiple loads. You have a multiple loads at your homes. So one of the loads is actually lightning loads. And if you see in your house itself that you have each house you have a certain lightning bulbs are there. So that also have multiple means power consuming units are there. Suppose your traditional bulbs, suppose incandescent bulb, they are actually through 100 watt, 50 watt. That kind of means bulbs were there. These are the small and the 200 are the larger bulbs. But the current scenario, if you see it, they are the very less power consuming loads are there. If you use LEDs or you are using trim lights or this powerful electronic interface based devices, this actually consume this 5 watt, 10 watt, maximum 12 watt, 20 watt, not more than that. But the you see the incandescent bulb, they consume very high amount of power. So they have to be replaced for the power consumption, reduction in the power consumption and the operating for energy saving as well. So first statement is true. Second statement is saying that energy intensive lighting system are left unchanged as they have no impact on the overall energy consumption. That is false because if you see that 200 watt, 100 watt, 50 watt, there are the high power consuming loads are there. If you use 200 multiplied by suppose you are 10 houses are there, they are utilizing 111. So it's come out to be 2 into 10 to the power 4 watt. Okay, 20 kilowatt is going inside of this light bulb as well only. So this is a huge concern. So this is a second next question related to the time of use. Time of use. Time of use. TOU is time of use. Okay, A is true. I've got one answer. Okay, A is true. Both, both I have got A as a true. Let read the statement. First statement saying that TOU pricing incentivize consumer to shift energy uses to off-peak hours by offering low electricity rate. That is true, because if you see this peak hours, this is a morning peak, and if you see this is the evening peak is there. So in the morning peak and the evening peak, their tariffs are high. Tariffs are high to motivate the customers to not utilize at that particular time. So, and the electricity tariffs are low in the off peak hours, so it's motivate the customer to operate in that. And the second is that first statement is true. Second is saying that utility companies mainly fix pricing regardless of the time of day, leading to the inconsistent energy consumption pattern. That is false, because utility companies don't have any access. Utility companies, suppose this is done through this discoms, not discoms. You can say that from the ministry as well, that they are involved in this designing of this TOU as well. So based upon that, this discount they utilizes that. So next question is related to energy benchmarking. So you please try this question. There are two statements are there. You have to tell me that which statements are true. Okay. Okay. I got one answer that may be A true. Or anybody else wanted to try? Okay. Again, let me explain you. First statement is saying energy benchmarking compares a building's energy performance to industry standard, allowing for targeted efficiency improvement. If you see some of the awards, such as the Griha Award is such that they give this 5-star rating to the houses. Okay, so if your house is less power consuming, is very low, they will assign you based upon that 5 star, that your house is such as you are not means consuming lot of power, your building itself, not energy appliances inside of the system. So energy benchmarking, this actually first statement is true. Is energy benchmarking is done to compare any building energy performance based upon that to industrial standard. Suppose I have stated that if this house consume 1 kilowatt only, okay, and with the capacity, it can also sending a power also to the grid. In that situation, it is a net positive. Okay, net positive is there, so it is consuming 1 kilowatt but sending 2 kilowatt. It means that it is a net power sending kind of system. So they can assign based upon that how much star they have to give. Okay, so this is kind of benchmark. And the second statement is saying that commercial buildings are exempted from the energy benchmarking requirement, so it does not yield any meaningful insight. That is false. They are not exempted with the benchmarking requirement. They each system, that's commercial building or residential building or any building, they have been checked. They also been checked that whether it is compliant with the energy benchmarking or not. This is next question. You have to tell me that which statements are true. Okay, I got one answer as A is true. Anybody else? Okay, that's the easy question. That smart grid technologies enable real-time monitoring and the control of the DERs, ensuring grid stability. B option is there. In renewable energy sources are incompatible with the smart. That is false, and leading to grid instability. That is false. Coming to the next question related to energy storage systems, you have to tell me that which statement are true and which are false. Okay, A is true. I got one answer. That A is true. Let's go to the solution part. That first statement saying energy storage system can quickly deploy storage energy to critical infrastructure, ensuring continuity of operation during emergencies. That is true. And the energy storage system are only used for cost optimization, have no role in emergency preparedness. That is false, because in emergency situation, when the grid is not there, then backup supply should come from the battery. This is the next question related to grid operation, operator struggle. So you have to tell me which statements are true. Okay, I got one. So that A is true. Let's go to this statement. First statement is saying that grid operators struggle to manage fluctuation in the renewable energy output, leading to grid instability and the reliability issue. Actually, this is true. This is true in what sense that this renewable sources, the RE generation is actually not constant. It's actually fluctuating. So you have no idea that when the speed will blow at a what speed. Suppose the generation you are expecting at a 10 meter per second of the wind speed at suppose at a 9 a.m. So what happened that it goes below one at say 2 meter per second, so it not generated that much. So there is a mismatch come. So this kind of thing is very struggling for this grid operator to manage this fluctuation. Second is that variable renewable energy sources have a negligible impact on the grid operator and do not apply. That is false. Coming to the next question. This question is related to demand side management, and you have to tell me that which statements are true or false. Okay, I got one answer as A is true. Both correct. Also, I've got. Okay, let's go to solution. First statement is saying that Demand side management programs incentivize consumers to reduce energy using uses during the peak hours through the price signaling and response initiative. That is true. Second statement is that utilities have no control over consumer energy uses pattern and cannot influence peak demand. That is false. False in what sense? Because I have told you that you have a critical loads are there. Critical loads and in the one house, and each house there are other houses as well, so they all are connected to one central controller. All, and also in house also you have a central controller which is communicating with they each appliances, and each appliance, this central controller this communicate with this central controller which is controlling the all the houses. So based upon this load curve, they actually manages this, okay, which load you have to switch off and which load you have to switch on at that particular. So utilities have also have control over the consumer energy as well. Okay, so this is the one of the statement you have to tell me. This is related to energy resilience. Okay, I got one answer as A is true. Anybody else? Shiv, Dharni, yeah, Devendra. Anybody? Okay. Let me explain you the statements. First statement is saying that energy resilience involve building redundancy and the backup system to withstand disruption and maintain continuous energy supply. Suppose you have two generators and they are needed to provide a supply to some loads. Okay, and you also kept one generator in the backup for the supplying this load, which is not at a full load, at a maximum load, but you can supply at a 50% load. And so this backup is, suppose this is a PG1 and PG2, so this backup supply is 0.5 times of PG1 plus PG2. Okay, so this rating backup generator. So if the any of the generation the PG1 is fails, so what amount of power you already have, that PG2 plus zero point 0.5 PG1 plus Pg2. So how much generators will be there? 1.5 tons of Pg2 plus zero point 0.5 Pg1. So this amount of power is available all the time. Okay. Suppose a generator 2 also fails, then you can supply this Pg zero point 0.5 times of Pg2 plus 1.5 times of Pg1. And if both fails, then you also have this Pg2. So sorry, Pg backup 0.5 times of Pg1 plus Pg2. So this amount kind of backup is needed, and this is also redundant system because you have already generating system, but you are redundant generating system which is half of the capacity of the both generator. So this involves this energy resilience. Okay, and in the second statement, what is telling that energy resilience is not a priority for utilities as disruptions are rare. That is false. Disruptions are not rare. It can come anytime, but you have to be prepared. Okay. Coming to the next question, that is related to interoperability. You have to tell me that which statements are true and which are false. Okay. I got one answer as A is true. Any other answers? Anybody else? Let me explain this question statements. First statement is saying that interoperability ensures seamless communication and the data exchange between the diverse energy management system, promoting efficiency and flexibility. Interoperability, this actually means you have a multiple types of connected systems are there. So operation of the multiple systems, suppose you have AC to DC, AC distribution generation system and the DC, and in between you have a connections as well, that is the DC to AC conversion. So interoperability means AC is operating with the DC and connected to the utility grid, or sorry, not here, here. So this kind of system have a interoperability that both the system can operate at a simultaneously time frame. So and so, but you need to have a communication between for the data exchange. So you have a central controller which can manages the how much power is to be transferred. So it also increases the efficiency and the flexibility. So you can operate AC here. You can also operate AC in the hybrid system also. You can operate with the DC system as well by using this AC DC converter. Okay. Second statement, what is telling that energy management system operate independently without any need for interoperability, leading to slide data and the efficiency. That is false, because it do not operate the independently without any prior need of the interoperability, because they need this system. Because the you don't know that when you are connecting the PV sources, suppose you are connected to HVDC system, then you can connect directly. In between, you only need this DC converter for feeding the extra voltage. So these are the other typical architectures were there. And do not want to go in the further because the time is 5:21. So if you have any doubt related to other systems, related to your academics or means competitive exams or anything, you can ask me just related to GATE or means this interview process of this IITs for the MTech or PhDs. You can ask me. You have we have 10 minutes. Anybody you want to ask? You can open your mic or you can write in the chat box also. There are couple of minutes are still left. So next lecture will be, I think not next. To next will be last session. Next session will be related to last year 12 week 12 assignment, and next to next is related to revision. Means 2 hour revision I have to take before the exam. So you
Hello?
wanted to ask anything related to your academics?
Sir, is my voice is clearly audible, sir?
Yeah, Dandi.
Huh, you are audible. Am I audible clearly, sir?
I'm audible now.
Huh. Actually, in
Yeah, yeah, yeah.
real-time
You are
projects,
audible.
I seen they will call utilities means we will construct the plant and we will send the power to the grid.
Hmm.
Um, and there will be SLDs
Okay.
who will maintain load shedding process, and according to the load power demand, they will do everything.
Hmm.
But
Okay.
uh,
So
in
there
one
are
of the
certain
question like
yeah, yeah, yeah. Please
utilities
continue.
will
Please
have
continue.
in according to the consumer demand they can control the power or not. It means you explain like there is a communication between utilities and uh, depends on the load curve we will generate power. But what is the meaning of utility? Whether in real time scenario they will call utility projects means like this only. Solar plant will be executed and they will send power to the substation, I think so. There SLDs will operate this all things. Load shedding process depends on the load curve demand. Asset management team will take care.
mm,
like that.
mm, mm. Yeah. So, okay, I got your question. Actually, the you are telling that it should be done through SLDC so that they can control the and manage the energy based upon that they using the load setting and other techniques. So actually, that central controller is at SLDC itself because the where the discom is there because of where the power is coming. It is coming from the your substation. Your substation is in command to that area, that power generating utility. Suppose there is a suppose in Mumbai you have a Tata Power is there. So Tata Power is the central utility provider, that is central discom, which provides the power to the each houses and the each commercial buildings itself. So that Tata Power will decide when to cut how much amount of power at what particular time, and how to shift and how to schedule the power from avoiding the any congestion itself. So SLDC is a central controller, so it is communicating with your home center controller if you have a smart controlling itself. And the second thing is that PV is also connected in a system, but the PV has a certain limit. In the UP, what they say that if you home power consumption, you have taken the meter. Suppose you offer 2 kilowatt rating meter is there, so you can install only 30%, means 300, not 30%. 30% means 30% of 2 means 600 watt PV plant you can install only. So in that situation also the discom is controlling everything. So your SLDC above that CLDC, those SLDC have power to manage and curtail during this load setting and all. Okay, between the demand and generation mismanagement.
Oh,
So
okay,
SLDC is
sir.
actually a
Means
central
utility means
controller.
up to SLDC we will call like utility only. Um, because
No, 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 no. Utility is actually a more broader system. Means this is substation is a one kind of unit, but the generating source is somewhere else. Suppose the generation is happening at a Gujarat. So from the Gujarat to this point is a kind of utility. So because the generating system is in Gujarat. So for that you have to do load flow analysis and all to
okay.
check whether the from where this
Uh,
power is coming,
okay.
from which place.
Normally, what I observed is we have agreement like we will send 70 megawatt continuously, but we don't know about the load demand anything else. From our switchyard, it will go 70 megawatts to the near substation. Uh, there, the control mechanism depends on the load, how they will
Okay.
control. SLDC will control like that I listen. But utilities, which we are the utilities, we will send 70 megawatts irrespective of the load.
Yeah.
We have agreement that we will send 70 megawatt at any time.
Yeah, there are actually the schedules are there because the day ahead scheduling should be done from the which generator how much power is to be taken from to the SLDC from the this distribution sources. So if the plant is there, so SLDC have a certain contract with them that at this point of time there we need this amount of power which is come from the day ahead schedule basis. So this they have to means supply this power at that
Yeah.
moment. But if they fail to
Uh,
supply, then they
yes, sir.
have
Yeah.
penalty
Thank you.
slabs are there. Yeah, yeah. Okay, okay. Anybody else having any doubt? Or, okay, then fine, guys. This. Thank you so much. I am ending this session. Okay, I will share the slides and this video on the link from where you can